Okay, good afternoon, everyone. I'm Ken Putra Lamiran, and this is my groupmate Divandika Jati Putra. We are from Binus University School of Computer Science. Here, our author that supervised Mr. Nicholas Hendrik Jeremy and Dr. Rio Sutoyo. Today, we'll be presenting about our project titled A Deep Learning Framework for Early Forest Fire Detection using a Computer Vision. Next. Okay, so wildfire have become increasingly severe around the world. In fact, in January 2025 alone, over 12,000 structures were burned in Southern California. So while the detection technologies have improved, many traditional methods still lack of real-time capabilities or struggle under challenging conditions. To address this issue, we propose a solution using computer vision, a field of artificial intelligence that enables systems to detect fire early and accurately. Next. So, based on the study by Lei et al. On 2024, which demonstrated how a lightweight YOLO V8 model achieved 92.3% accuracy and real-time speed over 30 FPS. However, their approach has some limitations, especially in detecting small fires in poor lighting. So in our project, it's built upon their work by improving the model selection, pre-processing, and evaluating different YOLO V8 variants like the YOLO V8M, S, and N to find the best fit for the real-time fire detection. So our main goal is to implement and evaluate a YOLO V8 based system for early forest fire detection. Here, we focus on building a cost-effective solution and achieving real-time inference with a minimum FPS of 30 FPS. So for the methodology, first, in the data collection, we started by collecting 2,509 fire and non-fire images from RoboFlow. So each of the image were resized to 640 by 640 pixels to ensure its consistency. The data is then processed to a ratio of 80 to 10 to 10 for train, split, and validation respectively. And next, we applied the image enhancement technique to sharpen details, reduce blur, and also to help minimize the false positives. And then for the model selection, we decided to select and compare three YOLO V8 variants, nano, small, and medium training, and testing them on a system equipped with a dedicated GPU.
Okay, moving on to the results. As you can see from the table, it shows for the three model that we tested, YOLO V8N, S, and M. The model performance metric that will be shown is the precision accuracy, recall, MAP at 0.5, MAP at 0.5 to 0.95, and the FPS. So from our table, our result shows interesting pattern. YOLO V8 at 8S or the small model achieve the best precision accuracy and also the MAP at 0.5 to 0.95 accuracy. This means that not only that the 8S achieve better in MAP, it will also achieve better in recall. However, even though it has a higher recall and MAP, the YOLO V8N outperform in recall and MAP at 0.5 and also the FPS during real-time prediction, reaching 58.4 FPS. However, the larger YOLO V8M model, despite its increased parameter count, fails to surpass the smaller models in performance across all the key metrics. This might be due to overfitting or also insufficient fine-tuning during training. So going back again for the nano model, this makes the nano model not only more accurate in real time, but also the most efficient. In real world testing, it accurately detects fire location using bounding boxes, all with fewer parameters than the other variants. This makes it ideal for use in resource limited devices like Raspberry Pi or Jetson Nano. Here is the analysis for YOLO V8N in real-time prediction and also static images. As you can see, as demonstrated, the YOLO V8 Nano variant performs exceptionally well in real-time prediction, accurately detecting and locating the fire instances with bounding boxes. The Nano model also achieved an average of 58.4 FPS during real-time inference, significantly outperforming the small and medium variants, which output lower FPS due to higher parameter counts. This superior efficiency and combined with its high precision and accuracy makes the Nano variant a preferred choice for practical use in resource-constrained environments. Thus, again, the Nano variant is the much preferred model for greater cost efficiency for smaller edge devices like the Raspberry Pi or NVIDIA Jetson Nano, since it has a lower parameter count, which means that it doesn't need a high-end system to run the YOLO V Nano model. So, to summarize our conclusion, our YOLO V8 based framework offers a strong balance of accuracy and efficiency. The Nano variant stands out with its 58.4 FPS with high precision and low computational costs, which mean that its practical and scalable solution includes more diverse scenarios like smoke and low light time images. We are also considering integrating temperature or sensor data for multimedia detection for our future works. So for our future works, not only that, we should also fine-tune our YOLO V8M model since it should outperform the YOLO V8S and also Nano in all key metrics, but it didn't in our result due to overfitting. So we should fix that in our future works. Thank you for listening to our presentation. Thank you.